everyone, we are live now.
Greetings to all. Greetings to all the esteemed speakers and the panelists in the session, and to our co-chairs, and also to the distinguished audience present in the session. We are on day two of the conference, and this is the session two of the day. I am A.K. Mittal, associated with TSDSI as advisor, Networks, Systems, and Technologies. And I will introduce you to the uh, co-chairs and about provide you certain inputs on the hygiene instructions. So can I have input? Yeah. So this is for information of all the participants here that everybody has been kept on mute on audio and video by default. And if you have any questions, please type them out in the Q&A tab, which is there on your panel. You can see it very clearly. Q&A is written there, and type their questions. So they will be picked up from there at the appropriate time when the turn comes for the Q&A. And after every keynote, there will be a Q&A session, and you can put your questions there. And you can also interact among those in the audience using the chat box. You can communicate to each other, and as there will be talks there, so normally it will be difficult to entertain questions put in the chat box. So please try to put in Q&A, and if possible we will try to pick up questions from the chat box also. And sometimes there is a difficulty in the channel bandwidth at some points where Wi-Fi or internet connection is not working properly, so you can switch from HD to the LD video. There is a button right at the bottom of the screen on the right side. You can use that, and you can expand your presentation or the screen by four arrows, expanding arrows on the right top corner of the presentation screen. So some other inputs are here on the screen, and these instructions are being put in the chat box for your further reference at any point during the session. Now, this day has been kept fully for 6G. In the morning, we had a session on AIML. Now, this is the second session of the day, which is the topic is 6G vision in air interfaces and network architectures, for which we have a uh, lineup of distinguished esteemed speakers. I am the convener, and the session co-chairs are Mr. Prakash R from CDOT and Mr. Samar Sharendra from Intel India. Let me introduce Mr. Prakash and um, Mr. Prakash and Mr. Samar. So Mr. Prakash is a Sirotian basically, and he is currently the study group study group networks chair in TSDSI and a technical expert in CDOT. He has been working as a researcher in the telecom industry for past 28 years, and his current interests include software-intensive telecom systems, wireless networks, 4G, 5G, and 6G, data networks, cloud computing, software-defined networks, etc. He is currently the coordinator for the following programs: 4G LTE radio, access network, ERP implementation, and he is a member of the Technology Roadmap Strategic Planning Group in CDOT. He is the IEEE senior member and ACM member and IET fellow. Now, let me introduce Mr. Samar Sharendra. Dr. Samar is a senior standards architect at Intel and the lead standards delegate at India and 3GPP SA6. SA6 is for application enablement and critical communication applications. He is also working as visiting professor at IIIT Bangalore. Prior to Intel, he was working as a research scientist at TCS and represented TCS at global standard bodies such as IETF, IEEE, and 1M2M. He has contributed significantly to research in multiple areas such as SDN, ICN, artificial intelligence, robotics, and drones. He has 20 plus patents and 35 plus published papers to his credit. So now I hand over the session to Mr. Prakash to introduce the session in detail and for rest of the conduct of the session. Thank you very much.
Okay. Thank you, Mr. Mittal. Thanks for the introduction and the overview. Welcome to everyone. TSGSI is, as you are aware, is a leading SDO in India. We are on peers with HC, TTA, and Airtes, and so on. We are a member of 3GPP. And there has been a lot of interest in 6G. In fact, a lot of people might have questions on how come 6G is getting started so early, because right just now the 5G rollout was started across the industry. But usually the technology development starts 8 to 10 years prior, and probably some of the leading R&D might start even before that. And I think India, we have always been chasing the technology, this time across the whole country, strategically across many departments, ministries, and industries, verticals. People are keen to get onto the bandwagon early so that we can become active participant. Towards that, today's workshop is focused on 6G, and today's session is specifically on 6G vision, the air interfaces, and the network architecture. And a lot of work has already been happening in ITU. A lot of people, companies, and countries come there, have been discussing and debating the visions. It's now our turn to listen to some of the experts here. I thank all the speakers who have joined it. And as a start, we have a total of five speakers. Each talk will be followed by a Q&A, but two of the speakers are, are on video mode. They could not make it online. Their video will be played out, so that sessions will not have a Q&A, but towards the end, the audience can raise questions, and I request all the other speakers to stay back till the end and respond to the audience Q&A. I also request speakers to check out the timelines and adhere to it, so that we are between sessions and it'll be good to close it within that time. Okay. And the first keynote will be from Mr. Joby George. The topic is exploring 6G vision and its key testing challenges. Mr. Joby is from Keysight Technologies. He's been working as a director of Keysight R&D, and is responsible for protocol carrier acceptance. Has more than 22 years of telecom experience and has worked with 3G standards from 2G to 5G, and currently in the mobile IoT space. And as a R&D director, he has more than 100 plus telecom engineers who work on the protocol carrier acceptance. And Keysight is one of the leading test equipment vendor and 3G compliant products. So we now move to, this is a video session, and I request the secretariat to play the video. Okay. So thank you.
Good afternoon to all. My name is Joby George. I'm working as a R&D manager and a director for Keysight Technologies. First of all, I would like to extend my thanks to TSTSI team for inviting me for this 6G Vision paper presentation. As the 5G market continues its rollout, our thoughts start shift towards a consideration for what the next generation of wireless technology will bring. On the journey from 2G to 5G, we have moved from connecting people to connecting things. Some are saying the vision for 6G can be summarized as being about connecting intelligence. To enable the 5G vision, we developed new radio technology, moved into new millimeter wave frequency bands, and added support for new use cases for new markets. For example, industrial control, satellite communication, etc. As we enter the 6G era, we can expect to follow a similar path with the new technologies, new frequency bands, new use cases, all coming together to enable a new vision for how we communicate. In this paper, I will be going in details on the enabling contribution from the technologies, RF frequencies, and use cases. Further go deep dive into some of the key developments and test challenges associated with it. We will also review and consider how Keysight can help overcome them and help industries to achieve 6G vision. As we discussed, we will go into some of the introductions and vision statements of 6G, and some of the use cases we will elaborate. Shortly visit on the timelines, go in some of the technological pillars and test challenges associated with it. As we all know, 5G is still evolving and is the network. 5G Advanced release 16, release 17 implementation is ongoing. We can see ultra reliability and low latency coming into picture now. So as the network disintegration is happening, virtualization, cloudification happening, 6G will be a quantum leap. And for example, we are going to add artificial intelligence and machine learning that will be built into the 6G. Let's look at the use case progression from 5G to 6G. Many will be familiar with the 5G triangle. Release 15 focused on enhanced mobile broadband. Now with release 16 and 17, we are adding new features to support URLLC. For massive machine type communication, we have added RedCap, but for best battery life, 4G NB IoT is still important. We can think about additional use cases like non-terrestrial network, which is using the low orbit satellites to enhance the coverage, and XR, which is using both vectors of enhanced mobile broadband as well as the URLLC, and adding AI as a service, artificial intelligence and machine learning is introduced in 5G as well. For 6G, several updated diagrams have been presented. Here, my particular spin on this. Here I show some new vectors, which is actually extended from the sides of the 5G triangle, sensing, low energy, and ubiquity. As we all know, the sub-terahertz frequency has a feature for sensing capability. So this can be used for sensing the surroundings of people. And then moving to the low energy, as we all know that current mobile operator network is real power hungry, and they are the main power users of a country. So this low energy is about moving towards the sustainability and network optimization to enable the network to operate in low energy. Then the third vector is about ubiquity. It's about full coverage and with the native trustworthiness and with the security. So, and then we are moving into a new dimension, taking all of these vectors into a new plane with the addition of artificial intelligence. So let us look now the different use case, starting with the enhanced human communication. Here the focus of 6G is to support a richer form of communication involving more of our human senses. We can think about this as increasing the overlap between the human world and the digital world. To achieve this, we need not just support the audio and video, but extend the communication to support haptic information such as touch, vibration, in addition with sensing capabilities from the sub-terahertz frequencies. Technology 6G will look into how we can use holographic imaging to create an image of a person who is not present in a room. So this kind of communication is called as 6G immersive communication. When we look at it firsthand, we feel that this is a revolution, but it's not. It's actually evolved from 2G to 5G. You can see that audio frequencies, we have introduced in 2G communication, which was required 8 to 32 kilobits per second speed. And in 3G, we moved to video. And further in 4G, we can see that mainstream mobile internet and enablement of this Web 2.0 helped social media, location, etc. In 4G time. In 5G, we are seeing XR, extended reality, and high accuracy positioning. Moving towards 6G, we will see the immersive cloud extended reality. This is nothing but you will be visualizing or watching a football match in the perspective of the referee who is in the field or a player in the field. As I already mentioned, haptic information such as sensors, the feedback on the sensors, vibrations, touch, all are captured here. And for an holographic display, as I already mentioned, it takes about 1 terabits per second bandwidth. So as we can see that moving from 2G to 6G, the human and digital world is overlapping much stronger. Let us look into our second use case, covering enhanced machine communication. Here we are seeking to create an overlap between the physical world and the digital world. Physical world and digital world. With support of the new technologies enabling real-time control, sensing of environment, position, and digital twinning, we are able to build a world where the network is able to interact with the real physical world, not just communicate or exchange data. So this is about control of cyber physical system. That is the vision of 6G, as well as this is of the industrial revolution referred as the Industry 4.0. In the future, we can have one single network that is able to support both real-time and non-real-time communication. Today, this is split into IT network as well as OT network. IT is nothing but information technology and OT is operational technology. Operational technology is real-time happening on the floor in factory. And information technology is nothing but communication and information together, which is a non-real-time communication. So this is used for controlling the real physical activities on the floor. So an example is that a robot is building a guided vehicle and moving materials around the factory. Industry 4.0 is being supported with some of the new features coming in 5G itself. In 6G, we have planned to add artificial intelligence to it and integrate both of this. That way, the current robots, which are autonomously working, will be changed to collaborative robots, which will act upon human instructions on real time. This requires high precision 3D positioning, real-time tracking, environmental sensing with the interactive mapping. For the third use case, we are looking into the digital healthcare. Here we add advanced services to the picture, what we have already built. With the addition, we can have cloud computing and data to provide services within vertical segments. We are showing healthcare as an example here, but it can be agriculture, it can be transportation or education. In this case, the vitals of the person has been collected and saved in a cloud server, and artificial intelligence or machine learning detects the irregularities in this pattern and inform that back to the human world or physical world to act upon it in real time. This is called the advanced services for 6G. So as I mentioned, this is not only for digital healthcare, it's for transportation or education or agriculture. Driverless cars are like kind of examples for this. And finally, we add the layer of native artificial intelligence and native trustworthiness on top of our diagram. Here we are using new machine learning technology to make the network more expansive, more efficient, thereby making some new use cases possible. For example, satellite coverage for ocean-based communication. In addition to the native trustworthiness, the devices to collaborate and share information within the distributed network, which will give more opportunities for artificial intelligence to improve the overall network performance. Thereby, we can also achieve the optimized network. Finally, we can use our full picture to develop a definition for 6G as connected intelligence of everything intersecting human, physical, and digital worlds. Okay, so we have looked at what 6G is and seen how exciting it could be. Let's look at when we might get it. The first step is to define the new use cases, which ITU is already doing. In parallel with this, we need to look at opportunities for new spectrum, which in some case we need to realize the vision. This is also happening today with the new World Radio Conference meeting planned for 2023. So we are expecting that 15 to 24 gigahertz and 100 to 250 gigahertz spectrum will be released for mobile communication usage by 2023. After the use cases and the new spectrum is agreed, we need to do further study and develop standards. So 3GPP is the standard development organization, which is already working on this. The current thinking is that release 21 will be the first release to include the implementation of 6G standards, which is about to come in 2027 or 29 timeline. This will lead to network rollout start around end of 2020s or early 2030. It is interesting when you look at the sister technologies to see how aligned their vision is with the 6G developments. The first wave of technology in the web, that is Web 1.0, we all know that it was focused more on the read-only materials, which had been published largely by the developers working on websites. With Web 2.0, the internet became read-write, and the social media, we were able to post. And you could see that mobile phones became the majority platform for folks wishing to post any content. As the web progresses to Web 3.0, we look at the goals of this technology. It is aligned with the 6G. Example, native AI, native trust, ubiquitous connectivity, the merging of human and physical worlds and in the real time. It is clear that both of these technologies are working together towards a shared vision. The same is also true with the Industry 4.0, which aligns with the advances being developed in 6G and the web. Some people are calling the term metaverse to describe this. This slide summarizes what is happening from a new spectrum perspective. The success of 5G has led to continued growth in data traffic across our networks worldwide. For 5G, we have the FR1 band covering around 450 megahertz to 7.125 gigahertz and the FR2 band covering 24 to 48 gigahertz. To support the capacity growth anticipated for 6G, more spectrum will be needed. In pursuit to that, industry is looking for bands covering all the way up to 24 gigahertz and trying to find new bands as well as looking to do refarming and band harmonization. In addition to the extending FR1 band, the industry is also looking for growing FR2 band and adding new sub-terahertz bands. The new sub-terahertz bands are especially interesting as they could enable much bigger bandwidth for very high throughput. As we have seen that holographic picture to transport, we may need 1 terabits per second, which is only possible with the sub-terahertz band. This also supports sensing applications such as precise positioning, imaging, and spectroscopy. Let us now look at the new technology which will be needed to support these new 6G use cases. This diagram is similar to one created within the European XIX project and referenced as 6 technology pillars, as have been described in the Huawei white paper. These show the technology pillars as artificial intelligence, sensing, and network sensing, extreme connectivity, integrated non-terrestrial network, security, and sustainability. Let us take one use case as an example, which we have already worked on, and look at which technology we need to support it. If we look at the enhanced human communication use case, which we presented, which is sometimes referred to as immersive communication, then we can look at use case and consider key requirements to support it. For example, low latency for real-time communication with which perhaps human senses, latency for real-time communication, and real-time touch information, controllable error distribution to accommodate the different modes of communication, holographic telepresence, and millimeter level imaging. We can then map new technology to these requirements to indicate what will be needed to support these use cases. For example, to support holographic telepresence, we need huge data rates, which can only be really be supported by sub-terahertz frequency. Yes, so also if you want to do accurate imaging, then we will need sensing capabilities supported by the sub-terahertz bands. Let's now look at a couple of these technologies and the test challenges associated with them. Use of sub-terahertz band is clearly seen as an important area for 6G. However, this band will bring with its significant technological and test challenges. Fundamental component work requires equipments which can support the measurements with the very high frequencies and wide bandwidths. We can see also that high data throughput measurement, validating that high data throughput by digital designs and supporting protocol stacks. This is going to be really challenging to test 1 terabits per second. In 5G, we have seen link budgeting, path loss was major challenge. And we have used high gain antennas for beam management. Such complex or more complex systems we may need for achieving these in the sub-terahertz frequencies. And as we can see that high precision mechanical specs are needed, like the position of a chamber, position of a chamber, 1 degree movement requires, it's like 3 micron of accuracy. So it's like 1/20th of the human hair accuracy we may need. So we can imagine such sophisticated equipments are needed for testing the sub-terahertz frequency and making this in a cost affordable to the industry is also challenging. This slide covers the artificial intelligence and machine learning related challenges. As we all know that the machine learning might replace the algorithms we currently use. So one of the example is testing PMI, that's based on the UE reporting the channel state indicator. So 5G, we were using a deterministic algorithm to operating both UE and network. However, this will be changed with the machine learning algorithm. So the challenges involved is what kind of test data we have for training the this algorithm. So availability of the training data is one challenge, and how much of data we need to train, whether one is sufficient, 10,000 or 1,000, we don't know. And the quality of the data is also important. Like we have to take the measurement from different areas, and then we need to train this algorithm. Otherwise, we will not be able to determine what is the pass or what is the fail, because pass cannot be real pass or fail cannot be real fail, because we wouldn't have trained that algorithm properly. With this, we have come to an end of this presentation. We have explored a model for showing 6G use cases as well as working through them to define a vision for 6G. We have also looked briefly at the timelines before reviewing what new technology 6G will bring to achieve the use cases. And the associated test challenges, couple of them we have discussed. And then Keysight, as a test and measurement company, we have been working in 5G and provided solution for these kind of challenges. And we are already working on 6G now. We will be providing a solution to overcome these test challenges for the industry. Thank you very much.
Okay. So that was a good overview. It's like a helicopter view of the 6G. And even though it was in the future, I think it laid out a good roadmap for us to keep track at a very high level. The next talk is by Professor Debarathi Sen, and the title of the talk is 6G Vision, Requirements and Challenges for Wireless Systems. And Debarathi Sen is currently an associate professor at IIT Kharagpur, India. She has more than 15 years of R&D and academic experience related to wireless and optical communications, and she includes interdisciplinary computing. Professor Sen has 18 patents to her credit and has published more than 100 papers in various journals and conferences. And Professor Sen is also a recipient of many awards. I'm not list them now, it is given there. And she is a senior member of IEEE, fellow of IE and IET. I now hand it over to you, Professor Sen, and look forward to a wonderful talk from you.
Thank you. Can I share my screen?
Yes, Professor Sen.
Can you see my screen?
It's just loading. Yes, we are able to see your screen.
Thank you. Good afternoon, everybody. So today my talk will be for the 6G wireless systems, the vision that currently worldwide we are having for it, the requirements for such kind of the system designs, and the challenges thereafter. As we all know that there are a couple of the bands which are currently under the consideration for the 6G wireless system design, and terahertz band which starts at the 1 terahertz only onwards, 100 gigahertz onwards, are one of the those promising bands for the designing such kind of the systems. We will see later on actually why we have come and chosen such kind of the terahertz bands for such kind of the applications of the 6C. If we see where are we looking for millimeter wave, we found our vision up to 2020, and today we are talking about a timeline about from 2025 to 2035 at least, where it is visions as a 6G, probably a 6G, and which will be filling up the gap beyond the 2020 societal as well as the business demands for the 5G, whatever we had to develop for ourselves, and we will be also keeping on going till we are getting the 6G in its full form. The fundamental requirements, if you see, that will suffice this dream, to fulfill this dream, are the new spectrum, some disruptive technologies. Networks are expected to be cell-less or cell-free. Disaggregation and the virtualization will be the heart of such systems. Energy efficiency, apart from the latency, very low latency. And obviously, artificial intelligence driven network and system design will be the prime driver. If I look today into the ITUT documents, already there are three most important driving characteristics being highlighted for upcoming technology. They are the high fidelity and holographic society. So holograms, multi-sense communications, and the next frontiers in the virtual mode of communication is becoming the prime mover. It is actually the, I should say, the exponential change that we have seen from 5G to the 6G is expected to be. Then connectivity for all the things. It's not only about the Internet of the things, it's about connectivity for all, physical world to your digital, to your cyber physical, and everything. And time sensitive or time engineered applications, timeliness for the information delivery will be very critical for us. I have pointed here the 8 different kind of the areas where the vision is matching with the actual requirements. For example, starting from the peak reliability to the latency to the mobility crossing 1000 km per hour for certain applications, to the network energy, to reliability, to connectivity and area capacity. So if I go ahead with this, so 8 different kind of the requirements are getting envises under the umbrella of 6G. One such use case is, if we try to see, we are trying to integrate the space integrated terrestrial networks, where the satellite communications are expected to be an integrated part of your terrestrial networks. Till 5G, we have separated out the terrestrial and non-terrestrial network and address their issues and the system design separately. 6G will be bringing the terrestrial and non-terrestrial networks also under a bigger domain. Sometimes the interplanetary communications also, some part of the world are also visualizing that to be a part of the 6G also. So the spectrum wise, if I go ahead, remember for 2020, we thought that we will be able to transmit 100 Gbps over wireless. That was the dream for 5G. For going ahead, we are targeting for ourselves at least 10 terabit per second over wireless. So it is not only the optical communication link, we are crossing that link to a bigger extent and fixing the target for the system engineers for 2035. And the traffic that we were going to be, the mobile devices will be 71% of the total traffic by 2022. And by 2030, we are going to have the data rate sufficient to complete the WAD broadband services. Then the prospects of the 6G terahertz communications, if I try to see, what are the typical things that we have to address? Foremost thing is the channel modeling, which currently worldwide it is going on, and we are not only trusting upon the field level experiments, but also actually some kind of the channel modeling. It is also getting addressed by the several research communities. We really cannot keep on going with the exhaustive channel measurements for all kind of the terrain. So the a sufficient amount of the modeling over the multipath channels are expected to be there for the system design to make happen. Physical communications will be also asking for the new advanced kind of the modulation and the coding techniques. The traditional modulation coding techniques will not be able to helping us to chase a data rate like 1 terabit per second and above. And hence the resource allocation, the ultramassive MIMO structures, enhanced beamforming, or I should say it is an AI-enabled beamforming. All those are the areas to be explored newly. To support such a high terabits per second data rate, definitely the networking part will be asking for another emerging solutions for it. Interference, medium access, alignment tracking, congestion control, routing, cross-layer frameworking, optimization, multi-layer optimization, again will be leading the networking part. Apart from that, definitely the interdisciplinary scenarios, we have already seen that in the 5G interdisciplinary communication was coming into picture. In order to include the space communications with our terrestrial communications, so interdisciplinary scenarios are already in the path of us. So joint radar and your communications, we call it a RADCOM, the joint sensing and imaging, joint sensing and communication, Internet of the Nano Things. These are some of the interdisciplinary scenarios which will be the prime important cases for our 6C research. Similarly, to support the system, we need actually the very deep research inside the device and the test beds. For example, all the power amplifiers, detectors, antenna and the arrays, power, your driver amplifiers, phase shifters, and also the physical experimental test beds, development of such test beds will be also very important for us. These challenges actually, there are several actually, though I have written here 12, if you explicitly divide them, the number may go up. But broadly, it can be classified into 3 parts: the architectural challenge, the technological challenge, and the social challenges. The architectural challenges will be addressing the 100% coverage with 100% reliability and with the similar data rate. It is not like that. They are the same age. You can expect a lower data rate, and in indoor you can expect a lower data rate in 6G. The AI-driven networking, AI-driven network customization, the best effort, SLA versus the best effort. These are all some architectural challenges expected to be addressed. Technological challenges will be about the area expansion, frequency expansion, also the radio wave usage expansion and all those. The frequency utilization, the carbon-free environment creation, the encryption, which is the network security driven by the quantum encryption, and your resilience, redundancy, recovery. These are some of the social challenges that we have to ensure. Security and the energy efficiency also will be a very, very important pillars for such kind of the system designs. Terahertz, why terahertz and why not actually the higher band of the millimeter wave? There are a lot of actually existing literature for supporting this kind of logic. And terahertz actually, there is a lot of plus points going ahead with it, because that kind of the data rate that we are targeting for, we understand actually, though the millimeter wave has given us a wide bandwidth, but you need a ultra wide bandwidth for supporting such kind of the data rates, hence terahertz. The availability of the bandwidth right now also is worldwide available in the lower terahertz zone. And remember, first of all, we have to release the sub-terahertz band, which is close to 140 gigahertz to 300 gigahertz cases. Beyond 300 gigahertz, we are currently visualizing as a phase 2 release for the terahertz communications. But terahertz brings actually a lot of the challenges with it. Very high path loss starting from the physical layer communication, a very high path loss, and high power terahertz band transceiver designs, ultra wideband antenna designs, frequency selective path loss, development of your novel modulation, transmission schemes, communication protocol. Yes, they are the challenges. To summarize, we have to revisit also sometimes our communication theory and our fundamentals of the communication theory for supporting such kind of the modulation, transmission, and coding designs. These are all required. And these are the available bandwidths for the terahertz that we are seeing, and we are mapping it with some kind of the sample applications in this slide in the macro cell. This is extension of that, and remember in future we will be talking about the Tera wireless local area networks, Tera wireless personal area networks, Tera secure terabit wireless communications or Tera secure communications, and next generation small cell networks we will be calling at the Terahertz nets. These are the kind of the some of detailing about all those applications that we can get out of these terabands. Terahertz will also enable to go ahead with the Internet of the Nano Things and the ultra high speed on chip communications that we were trying to design since long back. I mean, on chip via the optical communication, on chip communications over the system on the chip communication system designs, system on chip designs, and over the multiple layers of the chip communication throughout without any wear. That was actually the target of since long back. Right, opening of this terahertz communication or terahertz bands for the wireless chip design case, it will bring a revolution in the wireless chip designs, on chip communication and system on chip designs also. This is a very rough architectural design and overview, some kind of the dream kind of architecture right now. But what I tried to show here is in the 4G Advanced and in the 5G, we have tried to separate out the control plane from the user plane in the network. We also brought the synchronization plane separately to expedite the throughput, to speed up the data rate also inside the network. What 6G will be bringing here is, apart from this end-to-end orchestration, it will also create a new plane which we'll be calling as the A plane or AI plane. This is artificial intelligence enabling. For that enabling, we have to create actually the AI plane operator in between. The positioning of this AI plane may be above actually the data network and below the C plane, or its positioning is not yet fixed. How it will be operationally fixing out, and how actually it will be operating for different use cases, I should say. But definitely the positioning of this plane with the software defined networking and application of this NFVs and end-to-end orchestration will bring a complete new architecture for our 6C at the back end. So these are actually some of the potential candidates for the 6Z. If we compare about the technology, data rate, range, power consumption, and network topologies, noise source, weather conditions, and the security over the multiple bands available, from millimeter wave to terahertz to infrared to visible light to ultraviolet. So I have highlighted the terahertz range to show the plus points in terms of the data rate mainly, because range wise also terahertz actually cannot give the more range compared to your millimeter wave, definitely. So the combination of the higher millimeter wave zone to the sub terahertz will be a combination to the first generation of the 6G deployments as per my understanding and my vision. So network topology will be also supporting the point-to-point and point-to-multipoint kind of the structure, which again actually upper millimeter wave and sub-terahertz zone is capable to support. If I look into the noise source also and the other cases like infrared to VLC to ultraviolet, they will be also coming up with the interference from the sunlight as well as ambient light cases, whereas your millimeter wave, high millimeter wave zone and sub-terahertz will be only getting inferred by the thermal noise and easy to handle in the system level design. The robustness against the weather conditions, again, millimeter wave and terahertz will be favorable for us from the system design perspective, where the infrared and higher will be the sensitive very much. Security wise also, we can do visible light communication also can give you us a very high security in terms of the point-to-point communications and in the enabling the 5-layer security in the communications, but that can also be enabled via the terahertz and higher millimeter wave area. These are some of the very fundamental look in the terahertz bands, where I have tried to understand that what actually will be the predominating factor when the actual electromagnetic wave will propagate in the terahertz range through the wireless domain. See, line of sight path we understood from the millimeter wave itself, that the line of sight is the best way because your channel will be sparse in the millimeter wave. Following the same thing, your terahertz also will be sparse, true, but non-line of sight path scattering and the diffraction will be the prominent factors which were not visible in the millimeter wave. We will be seeing here again the spreading loss, the molecular absorption loss, oxygen and water molecules account for the most of the losses. And it is about your the choice of the band over which you can control some of these absorptions also from the environment. But one most important thing is that the scattering and the diffraction, which were not taken account in the millimeter wave conditions, and we have not seen those effects also because the transmission frequency was very low, which will be dominating factor here, and hence actually the receipt power level are further getting expected to be reduced. And if I see from the rain attenuation, that actually will be not that much causing an additional attenuation in case of close to 100 gigahertz and 140 up to 140 gigahertz kind of the environment. There are several other bands like 120, 183, 325 and 380 gigahertz bands where the different kind of the atmospheric losses can be visualized if I go above. And so actually it is just about the optimal choice of the bands in the above the wide range of the terahertz bands available. That should be matched with the kind of the applications we are targeting for. But multiple such pockets can be chosen for our system design. So this is again the summarization of the different frequency ranges and some contiguous band availability. As expected, if we go beyond 300 gigahertz, the contiguous bandwidth that is available for the application is increasing. But this is a dream today. We have no idea whether device will be available one day for beyond 300 gigahertz zone of communication or not. That future will answer. But till 300, we have the contiguous bandwidth of approximately 40 to 50 within that zone. That also depending upon the typical kind of the absorptions of the atmospheric losses we have to choose. But flatly, in a flat sense, we can see that a channel bandwidth of 2 gigahertz at least in a contiguous fashion we can get in the sub-terahertz bands. So if we center around 140 gigahertz kind of applications, you can get around 6 channels, each of 2 gigahertz wide for your system design. And each of them are helping you to get around 4 gigabit data rates. So you can roughly target about 24 gigabit data rates, which is far ahead from your millimeter wave cases. For higher modulation coding schemes, with higher modulation coding schemes, this data rate can be targeted at very high. These are some of the further terahertz wave propagation characteristics. I am not going in details, but it further actually is very helpful for the system designers to understand actually that how this atmospheric loss versus the diffusion scattering versus the specular reflections versus the line of sight probability to the weather influences can be balanced out. So what are the impacts coming on typically on the terahertz and the other terahertz versus other lower bands expressions, and how the system design can be made robust with respect to all these different effects. This actually terabit per second speed, if we wish to have it with a single user MIMO capacity, where the CDF is, this is a drawing for the cumulative distribution function for the getting a 1 terabit data rate over the air. And we were trying to understand actually what are typical kind of SNR required in order to get such kind of 1 terabit per second kind of the data rate over the air if I am having a single user MIMO capacity. And remember, this experiment was done with the 4096 base station antennas. And as we are in the terahertz, we can dream of actually making such a ultra massive antenna array structure in the terahertz band. See, actually with a 10 dB SNR, it is possible to at least achieve a 1 terabit per second operating point over the air. These are some of actually the typical outdoor terahertz channels that, and we tried to go ahead with the different kind of the modeling of it. And people have also done some kind of the outdoor experiments trying to see that the successful reception is really possible between a terahertz zone of the ultramassive MIMO outdoor channel cases. All these current channel measurement campaigns are going ahead with the kind of the horn sectorized antennas. It's not actually the array structure of the antennas. We are still waiting for it, which will further enhance the incoming signals quality as well as enhancing the data rate for us. 2-3 things I would like to mention about this slide about the multiple antenna techniques that we have to come up with. So this holographic MIMO, which is we are talking as HMIMO, or the large intelligent surfaces that are expected to be deployed in the environment in order to achieve this very high data rate in the future. The reconfigurable intelligent surfaces, which we are actually basically, it will be helping us to direct the beams towards the typical directions, controlled by a passive controller from the base stations. We will be able to go ahead with a higher range also. Apart from that, extremely large aperture arrays that are also expected to come for the outdoor antennas and outdoor applications, where the whole building structure and the outside of the building, a very tall buildings in the cities, are expected to be acting as a large aperture array antennas by themselves. So it is not true that always we will have to confine for the terahertz, sub-terahertz applications. We need not to only confine within the indoor applications only. With the advancement of this HMIMO or ELLA or RIS and the dimension of it, we can target also the sufficient amount of the outdoor coverage and enhance outdoor communication also. This also talks about again the support of the ultramassive MIMO systems, that some of the experiments that we have done in the simulation platform at our ends. And the multiple antenna techniques that we have changed, we have tried to also integrate the different mobility inside the users, multiple user situations, and try to find out the optimal size of this IRS, and also the activity patterns and the time. Also, the important part was actually the time resolution that you need to find out to steer your beams towards the multiple users and creating the interference-free multi-user communications involving IRS for the terahertz communications. This actually is another different kind of thought process that I thought to be addressed here. Remember actually the far field assumptions that we do for our up to 5G communication system with a large antenna array cases. If I go for this HMIMO or the LIS or the ELA cases, the distance for considering the far field assumption to the near field assumptions, we find actually even the distance or sufficient distance up to which your reasonable terahertz communication is possible, within that range, your far field assumption, even the far field assumption is not coming. It's breaking down. So you will be always, most of the time, you will be inside the near field communications where the assumptions for your planar wave propagation, that will not be considered. If the planar wave propagation cannot be considered, definitely actually then the incoming arrays, incoming rays, the propagation of the incoming rays which are falling on the huge array structure will not have the planar array with the planar wave structures, and hence you will be having a huge number of the deviation over the arrival rates, angle of arrivals across the whole antenna array structure, starting from the beginning to the last antenna array elements, which actually from the signal processing perspective will give the maximum challenge to be addressed in terms of your DO estimation, to be addressed in terms of your timing synchronization, as well as actually the time versus your Doppler synchronizations, time versus your frequency synchronization, time versus your angle synchronizations. So the very nice signal processing challenges are coming up because of this very unique and very challenging propagation from the environment itself in the terahertz coming up. So, as we have mentioned, that we are understanding that the wavedim is a key mover for our technology side from 4G to the 5G. But going ahead for the terahertz frequencies for this such kind of very high data rate, and also to address the very high vehicular speeds for some of the applications, we cannot proceed with the wavedim alone in future. We have to search for the new waveforms and orthogonal time frequency space modulation schemes, or TFS, or the OAM, orbital angular momentum kind of the technology, the kind of the modulation schemes they can, and non-orthogonal NOMA combined with the wavedim also can be thought of for another possibility for future modulation schemes. These are
Professor
some
Sen, you will have to summarize and close.
Sure.
Okay, cool.
So this is some of the modulation schemes that we can thought of, and their plus points and minus points are described here. One last thing that I would like to mention is about remember for the ultra wideband communication that we are talking in the terahertz, because of these ultra massive arrays, we will be seeing a very nice effect called dual wideband effects. It is a spatial wise, the angle of arrival will not be same. So, and over also the frequency wise, over the frequency, if you try to see the angle of arrival, that will be also typically changes. Telling in a layman's language, over the multiple frequency subcarriers of an OFDM, you will be seeing that the different angle of arrivals are happening. So we call it a dual wideband effect for any ultra wideband communication systems, and there is actually a very nice way out to how to now compensate this dual wideband effects in the system design for your terahertz will be a very nice challenge. So these are the different challenges that I have referred. Thank you.
Thank you, Professor Sen. That was quite an in-depth brief on the air interface, specifically on the spectrum aspects. There's one question by Subhash Chen, one of the audience here. So the question is, I'll probably ask it to you, but others can also pitch in. 6G would be an extension of 5G with sub-millisecond latency requirements. What use cases will it be useful, and how can this add to the economy? Would you like to comment? I mean,
what are those use cases? Can I see can you please scroll down? Can I see the question completely?
Yeah, this is the question.
Something is missing. What are those use cases that would be possibly only in 6G, and how 6G? Next line.
6G, how do you think 6G can add to the economy? Okay, to the use cases. So maybe you could take care of the use cases aspect.
Yeah, see, actually, sub-millisecond latency requirements means we are going towards the real-time transmissions. So all the real-time video, the real-time, any video transmissions, real-time, any kind of the communications, even this hologram, and then real-time presentations of a person everywhere. Actually, whenever you are trying to go at a millisecond latency, basically you are talking about real-time transmissions. So those use cases, all such kind of the use cases are expected to be under the 6G communication systems. And economy-wise, yes, it will be going ahead with a huge effect on it, because real-time video transmissions actually will solve a lot of our actually saving in some cases. For example, take an example of this typical workshop and this typical conferences worldwide that where we are running. So, absence of any particular speaker, that can be completely separated out, and all the kind of the real-time publications and real-time presentations to them, and all the explanation to the communication to the typical audiences, that all can be possible. Talk about medical world, any operation that are running in a high-tech multi-super specialty clinic. The doctor's real-time operation can be replicated. Even a situation in a village or in a sub-village and sub-area domain where the medical facility is not like that way. So,
okay. Thank you, Professor Sen. We now move on to the next speaker. The speaker is Professor Özlem Tukfe Demir. Okay, my apologies if I didn't get the name right. Okay,
yes.
she is from Top University of Economics and Technology from Turkey, and she's done her BS, MS, and PhD in electrical engineering from the Middle East Technical University. She is currently the assistant professor in Department of Electrical Engineering at Top Economics and Technical University, Turkey. Her interests involve focus on signal processing optimization in wireless communications, massive MIMO, cell-free massive MIMO, beyond 5G multiple antenna technologies, reconfigurable intelligent services, machine learning for communications, and green mobile networks, which sort of puts all in the bracket of 6G and quite in our interest. And we thank Professor Demir to agreeing to give this talk. And we reached out to various experts and they referred Professor Demir, and we are happy to have you here. And TSGSI,
Thank you very
I
much.
hope this is the start, and we look forward to more engagement with you. Now handing over to you and look forward to your talk, Professor Demir.
Thank you very much. And I'm sharing my screen now. This, I hope you can see my screen now in PowerPoint
Yes.
mode.
We
Great.
can see your screen and you
and
are audible.
from the very beginning, I can also use pointer. And thank you very much. Good afternoon, everyone. And thank you for the actually inviting me to the team, TSDSI team, and for this nice organization. Today, I will mainly talk about a specific infrastructure, which is one of the promising architectures also beyond 5G and 6G. It is cell-free massive MIMO, the cellless architecture combined with the benefits of massive MIMO technology, and mainly the physical layer aspects of this technology on top of the cloud run architectures for the futuristic implementation. And there are several open research questions and several implementation issues actually for a futuristic implementation. But in our book, in our first textbook on self-reading massive MIMO, we have outlined the basics of physical layer foundations of user-centric self-reading massive MIMO with a special emphasis on the scalability issues and covered mainly the frontal transport and this access point processing aspects of the user-centric self-reading massive MIMO. So mainly I will give a high-level outline of the physical layer foundations of this technology, mainly following our book. And let's start with the cellular networks, the motivation behind it, and how it is like actually meeting our demands in the past and currently also. Here you see a 4-cell structure, and I will use access points since in the self-read structure I will continue with the low-cost access points, relatively small number of access points. I'm calling the base stations as also access points in my talk. And you see the traditional cellular architecture here. And this architecture designed for mobile telephony. And initially, due to the design perspective, it is inherently scalable. So when a new cell is added to the system, a new access point is added to the system, a new base station, and again, the performance of the other systems, if the interference control is handled properly, is not affected, and the processing complexity of the other systems is not increasing. So it is inherently scalable, and also we can adjust it, make it denser according to the traffic density, and there are several actually very well performing interference control mechanisms. But the thing is that these traditional cellular networks were designed initially for voice communication, where the data requirement actually it's not so high. It is 100 kilobit per second is sufficiently enough for a good quality of voice. And here on the left part, you see the actually report from Ericsson's report and how data and voice communications, the needs for them are increasing with respect to the time. And now compared to the voice communication, data communication is the main part, and the data service requirement also is very high, significantly higher than the voice requirements. But the problem is now in the past it was not a problem for voice communication, but now for the data communication is the dominant communication in the cellular systems. The problem is the large data rate variations. Here you see a very, just for visualization purpose, a very simplistic view of how the data rate for a single user in a 4-cell system, and in each cell there is an access point with a single antenna, and due to maximum rate requirement, this data rate 80 megabits per second, there is a flat region here, and it just how decays with respect to the distance. And there are some regions, the cell edge regions, where the data rate is very small, and it is problematic. So this is due to the large pet loss. Although there is no interference in this graph, the effect with the interference becomes more challenging. And so the main goal of the next generation mobile communications is rather than increasing peak data rates to solve this issue, data rate variation issue, actually uninterrupted data service almost everywhere, because now everywhere we needed data communication with significantly high data rate. So not only focusing on the center of the cell, but everywhere uninterrupted. One actually step for this aim was the massive MIMO technology, and now since the beginning of the first seminal paper in 2010 by Marzetta, now it's in the standards of 5G. And the thing is that we benefit from special multiplexing and beamforming gains together in cellular massive MIMO. Now at each base station, or I'm calling access point, at each access point there are multiple antennas, many number of antennas, and it is like normally thought that like larger than or equal to 64 antennas. And with this larger number of antennas and simple processing behind this massive MIMO operation, special multiplexing is possible, and multiple users can be served simultaneously using the same time frequency resources. But the problem is that still we have large data rate variations. And now on the right figure, you see how these data rate variations for a single user, just for a single user, distance dependent, also neglecting shadowing or other effects, can be represented. Of course, there is a significant gain, especially in the cell center, but still there are large data rate variations, and this can affect the network performance badly. So actually our ambition is to create something like in this right figure. So everywhere the data rate is very high. And also to achieve this, we need some methods. The one thing is that we need to somehow need dense deployment of the low-cost access points to increase the macro diversity. In the left figure, you see this actually. Now there is a single antenna access points, but in totally there are 64 antennas 8 by 8 in this region. But still there are large data rate variations with this densification. The thing is that still the structure is the cellular. So one access point is serving, one user is only served by one access point. Normally the best channel gain access point, the closest one, or if there is shadowing, the best channel gain. But the thing is that how we benefit from the cell-less architecture, cell-free architecture, and joint processing, joint serving facility of the cell-free operation, combined with the massive MIMO approach. Now there are low-cost access points. The number of antennas at each access point is relatively small. But in total, if we benefit from joint transmission, we can benefit from both macro diversity, and also we can avoid now this cell edge issue, cell boundaries, because now there are multiple access points serving a single user. And that's the idea initiates the self-read massive MIMO. But in the original papers, self-read massive MIMO is thought of as like all access points in the network area serves all users in the area. So each them cooperatively actually work together in the very original papers. But this is not scalable. I will come to that point. But in our textbook, we define the self-read massive MIMO as an intersection point. From the ultra-dense network, it uses three important technology components. First of all, ultra-dense network to benefit from macro diversity and now less severe channel effects. And also this joint transmission. It is like in the coordinated multipoint, but there are some differences here. The signal processing and frontal transport aspects are more simpler compared to the 4G attempts. And here we benefit from physical layer aspects, physical layer benefits of cellular massive MIMO, which is already in mature form. And here you see now there is a network, self-read network, and there are L access points jointly serving all the users. And each access point has a fairly small number of antennas. Here we show it by N. And there are some users, but the number of users is much less than the number of available access points. So we are in the massive MIMO operating region. And also the important thing is that to facilitate this joint processing, joint transmission and reception, the access points are interconnected via frontal connections to one or multiple central processing units, CPUs. These CPUs can be either a big macro base station or maybe as a separate entity. So you can think of them as a logical entity here, but they are responsible for coordinating this self-read operation, self-read massive MIMO operation. But the thing is that now the scalability is the problem, because in the traditional cellular structure, they were inherently scalable. But now we are saying that if all access points serving all users, it is of course not scalable network. But the first thing we can do is a network-centric clustering, as done in the 4G attempts. But it was the main approach, but not successful from the self-read perspective. Because now, of course, again, there are, in this green region, for example, these three access points serve these two users simultaneously, jointly. But again, now the cluster edge issues appear, not cell edge issues, but cluster edge issues. When a user appears in the network and the cluster edge, then it is problematic. So we need somehow user-centric clustering, although it is more complex in terms of implementation. From the physical layer performance, we show its advantages, and the thing is that now each user is in the center, and the serving access points surround each user, and now this is also in line with the self-read philosophy. And also, when we look at the structure of the self-read physical layer, starting from the radio site access points and going to with the frontal connections to the CPUs, later the higher layers appear. But when we look at them, we can see the similarity with the CRAN architecture. So CRAN architecture is inherently suitable for this self-read massive MIMO, futuristic self-read massive MIMO implementation. And also here you see some shaded colored regions. These are the actually represent the user-centric clustering. And since they are determined based on the specific user needs, they are potentially overlapping, actually. These regions are overlapping. That's the idea behind the user-centric clustering. And there is an important thing we take also into account in our book. Critically, the thing is that if the number of users that are served by each access point is finite, when the total number of users in the area, user equipments in the network area goes to infinity, then we show that signal processing and frontal signaling load per access point is scalable. So if we can also devise a scalable power allocation algorithm, I will not go into the details, then the physical layer side is scalable according to the user-centric self-read massive MIMO we are outlining here. And the thing is that, now the important thing is that, again, the number of users that are served by each access point should be limited. Not all access points serving all users, but we will carefully select them. And I will go into the basically two operation modes of self-read massive MIMO in both uplink and downlink. The first one is the centralized operation. The second one is the distributed operation. And in the centralized operation, let's start with the uplink, because in the self-healing massive MIMO, in the canonical form of the massive MIMO, time division duplex is adopted here. And in the uplink, both data and pilots are transmitted. And uplink pilots, thanks to the this channel hardening effect, is enough. Most of the time, it's enough for the downlink pre-coding, and there is no need for downlink pilots. And that's the main idea also in massive MIMO. It's not proportional to the number of antennas, these pilots. So the thing is that during uplink in the centralized operation, access points, they are just act as relays, like remote radio heads. So they are getting the signals, and maybe in some initial RF processing in their very small dedicated hardware, and then they send the received signals to the CPU. Of course, here we assume the full synchronization is available, and it is one of the also challenges in the futuristic implementation. But here, when we look at from this side, the centralized processing is possible using all the channels, all the related channels in a scalable manner. The important thing is that. And the data detection, the other centralized receive combining, is done at the CPU. Similarly, in the downlink, also the access points are just acting as relays. Just they get the signal, transmitted signal from the CPU, and they just transmit it. Maybe after some initial RF operations again. So this data encoding and centralized transmit pre-coding using all channel estimates are implemented at the CPU. When it comes to distributed operation, now its performance is of course expected to be worse than the centralized operation in terms of spectral efficiency, because now the channel estimation is locally implemented at each access point. Then after these local channel estimates, also locally receive combining and transmit pre-coding is applied. So these are just based on the local processing. And the CPU is just responsible for the final data detection and maybe some more additional layer of processing using the large-scale statistical information. And we call it large-scale decoding. And the thing is that in the data encoding, it is also responsible for the data encoding part. And when we look at the comparison to the cellular massive MIMO and small cell, here you see the performance in the uplink. And for the cellular massive MIMO, these are just the combining scheme we use, and it is the best among the alternatives. And the small cell, in the small cell, cellular massive MIMO, there are 4 cells, mainly 4 cells, and in each cell there are 100 antennas now at each access point. So the total number of antennas for all the schemes are the same. And the thing is that just the architecture here changes. In the second figure, there are less number of access points in the self-healing massive MIMO and also small cell, but a larger number of antennas at each access point. And we are here comparing both centralized and distributed operation, also with the best processing schemes in small cell, where there is only one access point serving each user, and also cellular massive MIMO. We benefit from the massive MIMO technology, but again, we have a cellular structure. And when we look at the cumulative distribution function of the spectral efficiency, we can see a significant gain, especially at the lower tails, where these worst case users, the unlucky users, they can benefit a lot from the centralized operation of the self-healing massive MIMO. When it comes to distributed operation, there is a drop, but still there is actually around 1.5 times improvement, more than 1 times improvement compared to the cellular massive MIMO and small cell system. But in the high tails, the small cell and cellular massive MIMO performs better than the distributed operation. So the centralized operation is the key. Somehow we need to approach the centralized operation. And in the other figure, since now there are small number of antennas, multiple antennas at each access point, small cell performance of small cell improves because now there is a local interference suppression capability. But still we see the improvements in the worst case users and also with the centralized operation for almost all the users. There is a significant improvement. And lastly, these were just some high-level introduction of the physical layer aspects. But in this paper, we have looked at the end-to-end network power consumption modeling by not taking into account only the radio side. Like here, I'm using this open run terminology. That's the reason now the access points are replaced by open radio units, and there are we are using time and wavelength division multiplex passive optical network. So there are optical network units, and we are these are connected to the with the frontal connection. We have optical splitter to the O cloud in the O-RAN cloud, and there is optical line terminal, and we benefit from the virtualization and sharing of the processing tasks. The thing is that in the O cloud. But the main idea is that we model the end-to-end network power consumption and look at how we can benefit from, also in terms of energy consumption, how we can benefit from turning off some access points when it comes to the energy saving of the full end-to-end network. And we jointly orchestrate the radio, frontal, and cloud resources and solve a difficult optimization problem. So that's the reason we look at a small, relatively small system. There are 16 access points and 8 users, because we solve the problem using the mixed integer programming techniques. But our aim is just to get some insights to understand the problem. Now, this figure is a bit complicated, but the thing is that there are two double y-axes. The left y-axis is the total power, and now you can see that this dashed line is for small cell, only one access point serving the user, but the other one is the self-free massive MIMO. And after some spectral efficiency requirement for all these 8 users, you don't see any result for small cell because it is not feasible. So in terms of guaranteeing the more attainable spectral efficiency, self-free massive MIMO, we know it is advantageous, but the interesting thing is that we can also aim at power saving by somehow smartly adjusting the number of active access points. Benefiting from joint transmission, we can reduce the number of active access points with this self-free massive MIMO structure. So now, here, for example, at this spectral efficiency value, we observe 14% power saving. And the other curves show the number of active access points, these O radio units, and the digital units in the O cloud. The digital units, so we see that less number of active access points and the digital units with the self-free network is possible, and we can also use this architecture for energy saving for a given requirement of spectral efficiency. And in conclusions, I just outlined in a high-level manner the physical layer foundations, and actually in several papers and in the related literature, there are now, it's in solid shape. The physical layer foundations are well established, but the thing is that how to deploy self-free massive MIMO functionality in a practical system is an important open problem by considering the end-to-end network architecture. And there are important open research questions in terms of this end-to-end network architecture, like promising network architectures. We are just only looking at the C-RAN architecture in a basic way. And also these low-cost frontal technologies. Now we assume these error-free wired frontal technologies, but how to benefit from other low-cost frontal technologies such as wireless technologies or combined fiber wireless technologies. And also there are lots of hardware impairments we need to take into account that can affect the performance. And the thing is that normally in these works, the initial works, since we are in the initial stage, normal snapshot-like static scenarios are considered, but in a dynamically varying traffic, how to design the optimization algorithms in a scalable manner, and also the energy saving mechanisms, which will be important in 6G. It's an important problem. And also a very important problem is this time and frequency synchronization in the C-RAN architecture, in this self-free massive MIMO architecture. And that's the end of my presentation. Thank you very much for your kind attention. Maybe I can either...
Thank you, Professor Demir. Thank you very much. Do we have some questions from the audience? Asif?
No question yet, sir. Ms.
Okay.
Ozna, you can unshare your screen.
Okay, okay, and it is like stop presenting.
Thank you.
Yes, now.
Thank
Okay, thank you very much.
Right. So, Product, can you bring up the? Thank you very much. Uh, So we have till now seen the speakers on the vision and the air interface of 6G. As the title of this session goes, the 6G air interface, vision, and the network architecture. The previous speakers have spoken about the vision. Mr. Joby spoke about the vision, and Professor Debarathi spoke about the terahertz frequencies, followed by Professor Debarathi. Very interesting talk about the cell-less communication. Now we move on the architecture side of it, and I would like to invite Dr. Richard, who is also my colleague at Intel, to talk about the network architecture. Dr. Richard is a senior principal engineer with Intel. He has overly 25 years of experience, and I believe since the inception of 3GPP, he is also involved with the standardization work. So that brings a lot of insights into what can go in, what should go in, and what are the reasons of that contributing all of that. He has also served at the 3GPP RAN 2 chair, which is a very important group as far as the 3GPP RAN interfaces are concerned. He is also involved with the 5G advanced and early 6G studies, and he is also contributing to the 3GPP RAN plenary. Dr. Richard has graduated from the University of Cambridge, United Kingdom, in Electrical and Information Sciences in 1993. So, with a big round of applause, I would invite Dr. Richard to take over this session and present his views.
Thank you very
You
much
can-
for the, yeah. Hope everybody can see and hear me. So thank you very much for the introduction. So as mentioned, we will have a slight shift, I think, from the previous presentations, and we will shift from talking about the radio interface, and I will focus far more on the network. So let me share my screen for you. Okay,
Yeah.
it seems that you have you can see my screen. Great. Okay, so I'd like to start here by saying a few words about the goals and challenges and indeed expectations for 6G. So there are 6G discussions now happening in many groups and fora, and indeed in conferences such as this one around the world. And one common theme that we hear with regards to the 6G system is that it will need to go beyond simply being a communication system. And it will need to encompass computing and intelligence and become a cloud native system. So as an example, 160 Fora, so the Next Gen Alliance, which is centered in the US and to which Intel is a contributor. So they have identified a 6G distributed cloud and communication system as one of what they refer their 6G audacious goals. So this convergence of computing and communication for 6G is very much the focus of what I will talk about today. Let's start a little bit by talking about a few of the drivers behind this. So the first driver I'd like to mention is growth. So despite seeing exponential growth in data volumes over recent years, we also see that there is a flattening in the revenue growth that is seen by the traditional cellular operators that are delivering mobile broadband services. And there is a need to find new drivers for growth, and new computing and cloud services are an exciting opportunity in this area. So a second driver that I'd like to mention briefly is sustainability. So there are many different sides to sustainability, but energy usage is one, and it is of increasing importance both from an environmental and also a financial cost perspective. Transporting data to be processed in some distant cloud data center has energy costs, and these can be minimized by processing data as close as possible to the source. And there are also other benefits, so delay benefits by also processing data as close to source as possible. And so this is a trend that, to some degree, that we already see today with cloud computing moving more out towards the edge. Other important trends that we see are the continued advancement of artificial intelligence and machine learning, and any future communications and computing platform will, of course, need to support these computationally intensive AI workloads. And then finally, a trend that we see today within the context of 5G systems is the cloudification of the network, with both the core network and the RAN being deployed in a virtualized manner on computing hardware. And this is the trend really that sets the groundwork for what we see as the next fundamental shift, which is from simply building a network in the cloud to the network actually becoming a distributed wide area cloud, which enables ubiquitous computing and intelligence. So let's, with this slide, start to dig into a little bit of what this transformation I've been mentioning it will really mean. So in the center of this figure, we have a representation of a 5G system. That system provides essentially one service, the communication service. To deliver that communication service, we have had three functional planes. There's the user plane handling the user data, control plane for handling control functions throughout the system, and a management plane for managing resources, etc. in the system. To transform the system into a 6G cloud that natively offers computing and data services alongside those traditional communication services, we envisage a new service planes being added to the system. So we have shown on this figure, we have a compute service plane and we have a data service plane. We also envisage that there will be a level of coupling needed between these different service planes, between the communications, compute and data service planes. And that coupling may be needed in order to ensure performance and scalability. And to provide this coupling, we show that the functional planes that already existed in 5G are now extended across also these new service planes as well. So perhaps trying to give a slightly more concrete example. So the management functional plane will have to jointly manage the resources for the communication service, the computing service, and the data services. We might also see traffic awareness in the user plane functions to enable us to optimize and prioritize, not just in communications itself, but in the communications, the computing, and the data services. So with a very simplistic example, you could imagine a situation where you have loaded resources in the system, and of course it makes sense to apply consistent prioritization across all of these different services. It wouldn't make sense to treat the communications aspect with very high priority, but then treat the computing on the payload with a very low priority, because overall the service to the user then is not being prioritized. So that's, I hope, gives a feel for why there needs to be this coupling between the different service planes. So in the previous slide, we talked about transforming the 5G system into a 6G system that natively provides computing services as well as communication services. In this slide, I'm showing that same 6G system, but alongside also the more traditional centralized data centers and regional edge data centers. All of these will have computing resources available and may offer computing services. And they all become part of one cloud. And the applications can exploit services offered from any of these locations as available and as appropriate for the particular application. So we even envisage that the end user device could have computing resources and services offered to other parts of the system. So computing workloads, they can be balanced across all of these locations as well as the end user device itself. And this is really what we mean by ubiquitous computing. Access to those computing resources across all parts of the system and the device itself. So this really goes beyond what we have today with networks being deployed in the cloud, and it will fundamentally transform the system from just a communication system to a coherent communication and computing system. So on this slide, I'd like to look at some service scenarios, and what I really mean here is who might be interested in subscribing to these new computing services offered by the 6G system. So the first scenario in the top left, so we show a mobile user or perhaps the mobile device vendor might be subscribing to 6G computing services. The 6G system provides infrastructure platform or software services. And the point to observe here is that the application is fully provided by the 6G system itself. In this particular case, there's nothing required from any kind of external cloud. Scenario 2 in the top right shows a case where the application provider is subscribing to the 6G computing services. So the application users will access the application based on their subscription to that particular application provider. And again, like in the first scenario, we have a situation where the 6G system provides all of the infrastructure platform and software services to the application. And again, there is nothing provided from an external cloud. In the third scenario, which is bottom left, so we now have a computing service provider as well, a CSP. And they are the ones now subscribing to the 6G computing services. So the 6G system provides infrastructure platform and or software services again, and it makes them available to the CSP. The CSP can exploit the resources and services offered by the 6G system as needed. And of course, that's in addition to their own resources and services that they have available. And of course, whether they choose to utilize resources from within their own cloud or within the 6G system, those are decisions that can be made, for example, based on performance, load management, etc. So from the end user point of view, they in this case might not be aware at all where their resources are coming from, whether it's actually being provided by the cloud service provider or by the 6G system. And then final scenario I'd like to describe is the one in the bottom right. So here the 6G system serves as a moderator for a multi-cloud solution. The 6G system can orchestrate and distribute computing workloads across the device, the 6G network itself, and also the resources offered by a number of different cloud service providers. This last one is I would say is the most ambitious scenario, and primarily because this requires different cloud service providers to cooperate with the 6G process in order to allow the 6G system to become that moderator between the providers in this multi-cloud environment. Okay, so if we go to the next slide, so I think it's actually a very reasonable question for someone to ask: is what is the difference between what we can enable today with 5G edge computing versus what might be available tomorrow with this vision of 6G ubiquitous computing? And so to address this question, we have here a comparison table to highlight some of the differences. So 5G edge computing is typically deployed as a regional edge data center or may be deployed as a private network on premises edge. It focuses on realizing the computing functionality, whereas the 6G wide area cloud aims at achieving a widely distributed computing across the device, the network, and the edge, and the well-centralized data centers. And scalability here is a foremost consideration. So a 5G edge computing typically works in an environment where we have a single ownership and security domain. So the edge is either part of the cloud service provider as cloud, or it is part of some on-premises edge system, typically a private system in that case. The 6G wide area cloud, in contrast, will encompass multiple security domains and multiple ownership domains across the device, the communication service provider, and the cloud service providers. So, and to achieve this, these multiple ownership domains, we are going to need standardized interfaces to ensure that there is interoperability. Then a 5G edge computing typically has abundant computing resources in the form of the regional data center. Computing resource availability is typically not a concern when we're performing service discovery and admission. And computing workload distribution typically happens at a large scale. In contrast, in the 6G wide area cloud, computing resources are often limited in each location. So computing resource availability now becomes a concern when we are doing service discovery and admission, and further complication occurs as a result of mobility and the workload dynamics that really amplify these issues of limited computing resources. So this point might seem a little bit counterintuitive to say that as we move from a 5G system to 6G, we have to start thinking about limited computing resources. But the key point to understand this is that what we are talking about is a very distributed computing resources, and hence that there will be some locations where the resources will have some limitation. It's not that the system as in total is necessarily having limited resources, but in some of the particular locations there will be limitations. And the system therefore needs to have mechanisms for dynamically distributing that workload and migrating workloads from one resource to another. So other differences, so 5G edge computing resides beyond the 5G mobile core network. So the control messages and the data traffic between the mobile devices and the edge computing servers, they all have to be transported as over-the-top traffic over the 5G system. In a 6G wide area cloud, the computing becomes part of the 6G system, and we can have a much tighter coupling between the communications and computing, especially from a control plane perspective. So 5G edge computing is really a scaled down version of the big data center cloud, which applies a similar design principles to data center cloud, such as centralized orchestration and control. And the scaling down does not really fit the 6G wide area cloud due to scalability issues. So we are going to need some new forms of cloud, and design principles will have to be developed. Okay, so let's moving to the next slide. We try to show here a couple of challenges that are going to be faced, not intended to imply that these are the only challenges. There will be many, but sorry, excuse me. Okay, so first challenge I'd like to talk about is that we will is that today we have completely separate domains controlling the communications and the computing. All access to the computing is over the top, i.e. that means that it's all carried over the communication system's user plane, and this adds complexity and will limit scalability. The mobile communication system and the cloud computing systems are conventionally independently designed, and over the years they have evolved independently. And this approach has worked well when the computing services have been centralized in a national or regional data center. The mobile network simply provides an IP anchor. In the case of 5G, this is the user plane function, or the UPF, and the 5G system provides a transport tunnel for the mobile devices. The cloud computing system provides over-the-top computing services, and the mobile network IP anchor selection and transport tunnel establishment are totally independent from the establishment of the computing service. So this decoupled principle faces challenges when the computing becomes more distributed. Both sides need close coordination with each other to achieve the benefit of distributed computing. So the mobile network needs to know the computing service location for a mobile device to select a proper IP anchor and for setting up the data tunnel with appropriately low latency. And the cloud computing system needs to know the location of the mobile device and the communication channel status in order to select a proper computing service with appropriate proximity. So to some degree, 5G edge computing started to look at these issues, but this sort of very much happened not at the beginning of 5G standardization, but at a later stage. And so, for example, it has some enhancements relating to enhanced DNS mechanisms and by the introduction of the Edge Enabler service. So in 6G, the goal is going to be to natively support ubiquitous computing services from the beginning of the system design. And in this way, by proper design from the start, we have an opportunity to enable much more effective coupling and interactions between the communications and the computing systems. Okay, another challenge we face is how to enable a dynamic device-to-network scaling and make the mobile device become a native part of this 6G cloud as well. So today's cloud computing relies typically on client-server applications. The workload partition between the device and the server sides are typically fixed, and they've often been predetermined at the point at which the application was developed. The main computation tasks typically are done on the server side, and then the device side often is just not much more than a user interface. The present client-server model works sufficiently for data center clouds, and we can safely assume that the data centers have unlimited computing resources to hold the server-side workload. However, the distributed computing and advances in device computing, some of what is currently the server-side workload could be held on high-end mobile devices or within network nodes. And here, at times, computing resources might be limited. The unlimited computing resource assumption we had previously is no longer valid. So we need dynamic computing scaling, or in other words, dynamic placement of where the computing workloads are located in order to adapt to these resource limitations and distributed computing. So factors such as the network condition, power budget, latency, etc., will all be inputs into making those decisions as to where to place the individual workloads. Okay, let's move on. So, let's move 2 slides at once. So, the 6G ubiquitous computing that I've been trying to explain in the previous slides is really the coming together of 2 different worlds. So we have the mobile systems world, which is the one that I come from, and also the cloud computing world. And these 2 worlds are going to need to work together and as a joint force to create a joint force of both the cloud computing technologies and the mobile system technologies in order to enable this 6G wide area clouds. So mobile systems, typically have very well-defined mechanisms for session management, mobility management, service continuity, authentication, interoperability, etc. And the mobile industry also has great experience of standardizing and building these systems at a global scale. The cloud system have well-defined technologies for orchestration, workload disaggregation and distribution, data management, etc. And we're going to need both of these, these skills and capabilities in order to enable the 6G wide area cloud. So this is coming to my final slide now. So I hope that in the limited time available, I've been able to describe a little of our vision for the 6G system, offering ubiquitous computing services as well as the more traditional communication services. There's a lot of work still to do, and there will be many questions that are not yet answered. So the questions on this slide are just a few that you might think of. I'm not going to go through all of them. Perhaps maybe just say a word about the standardization question, as standardization is very much my own personal background, and therefore it's a question that is of particular interest to me. So 3GPP has been very successful in standardizing now 3 generations of communication technology, and these have all been deployed by the wider telecoms industry with huge success around the world. To transform the system to a communications compute data system, offering this ubiquitous computing, will be a new challenge for 3GPP, and it's likely to require it to have to work with a number of bodies and fora that it has not previously had the need to work with, and potentially these bodies may have quite different working models, and this is going to be certainly an interesting challenge going forward. And then I'd like to end with just a final comment on the expectations for 6G. So we've had many generations from 2G, 3G, 4G, 5G that have all been communication systems where we have continuously been increasing the KPIs for radio performance, whether that be data rate, spectral efficiency, latency, or whatever. So in our view, 6G should not simply be another iteration of this process, i.e. a communication system with radio KPIs shifted up a notch compared to the previous generation. It's important not to misunderstand this point. So improvements to radio performance will still be relevant, and indeed they will still be very important. But we believe that in addition, it's going to be critical for the ongoing success of the industry to shift focus a little, go beyond just communication, and move from a communication-centric system to a communication computing data-centric system that can natively offer computing services together with those communication services. Okay, so with that, I'd like to conclude my presentation. So thank you very much, everybody, for your attention. Thank you.
Thank you very much. Thank you, Dr. Richard, for a fantastic presentation and very insightful that how the system should emerge and how that mobile network can converge with the cloud network and give a new architecture for 6G, which is probably bring all the insights in terms of the better throughput, latencies, and a new system architecture altogether, unlike the today's, which is just an evolution probably. Anyway, so I would encourage all the users to pose the question. I see there was a question for Professor Demir earlier, but she has responded to very well. There are a couple of more questions for Dr. Burbage. So, Asif, can you bring up the question, please?
Sir, one more question from Mr. Prakash. I can show on the stage. And one raised hand from Mr. Vijay Roy. So one by one, you can take that.
Right. So, Dr. Richard, can you see the question?
Yes, I can. So maybe I can try to answer. So the question is about sensing and storage in addition to communication and compute. So I think from what I talked about, actually, most of what I talked about was the communication and computing side. On that, I think it was the second slide I showed, there was also what we had shown, which was a data service plane. And this data service plane is I would describe it as, this encompasses data storage as one element, but also encompasses data collection. So, for example, the sensing type applications, which are about data collection, could well fall into this part of it. So certainly those things such as storage and data collection, such as sensing, they certainly form a part of the new service opportunities that we see for the 6G system.
There is another question: impact of storage on the top of the same question.
I I think Asif Richard has already handled that. Mr. Prakash, if you have a follow-up question, please let us know. In the meantime, can we enable the microphone for Mr. Vijay from TEC? Is that possible, Asif?
Yes, we can. Mr. Richard, can you unshare your screen?
Yes, certainly. Yeah.
Thank you so much.
Okay. Thank you.
Yeah, I've invited on stage. I think he is on stage now. Mr. Vijay Kumar, can you hear us?
Are you able to hear me?
Yeah, we can hear you.
Yeah,
Thank
Mr.
you, Mr. Richard, for your beautiful presentation. And we also feel that ubiquitous, or we can say pervasive, distributed intelligence is the prerequisite for 5G. Without intelligence, we cannot even think of going beyond the Shannon-Hartley law if it is required. So this is a very much requirement. So again, I have seen in the final slide that the challenge, I think the open RAN, disaggregated RAN is must for the 6G. What is your feeling for that? Because disaggregation will enable the distributed or pervasive intelligence everywhere. That is my view. What is your opinion, Mr. Richard? Thank you very much.
Yeah, thank you. Yeah, so I think certainly. So I think we already have seen in 5G today. We already sort of started on this journey of virtualizing the RAN, and so that's essentially meaning that we put the RAN functionality onto more generic compute hardware, and then on top of that, there's the disaggregation of the RAM, which means the ability to distribute some of those RAN functions in across more different parts of the system and introduce standardized interfaces between them. So I think this is going to be a continued trend. I think this actually is this transition to moving to a virtualized RAN is really the sort of maybe starting point for what we've talked about in my presentation. We now have a RAN which has a lot of generic compute capability in it, and so the question comes, well, why not make that compute capability available, not just for the RAN functions themselves, but for other uses, and make it available as a more generic service to other applications and users. So I think they are, I think virtualized RAN, disaggregation of the RAN, they are very much, an integral part of the story that we've been talking about.
Rather, I should like to say this is a prerequisite for 6G. Am I right or wrong?
I think in our view, the answer would be yes. Absolutely. I think the virtualization of the RAN is definitely a prerequisite for 6G. But I think there could well be others with a different view, right?
When we see the for the example 7.2x split, we can see we have mainly very little of the hardware with a lot of computational capability and availability. So that will certainly, I think, provide the vision for the 6G. Vision means distributed intelligence, distributed computation, ubiquitous computation, that will be possible. So I think, in my opinion, to the maximum extent, this is the prerequisite. This is my view. I think you are
Yeah.
also
Yeah,
agree.
Yeah.
Mr.
I'm in
Vijay
agreement with you
and
essentially. Yes.
sorry to interrupt, Dr. Richard and Mr. Vijay. Sorry, we are running severely out of time. We have one more presentation to cover.
Thank you. Thank you.
I would really encourage to write down the question on the Q&A. And Dr. Richard, there is some questions for you already on the Q&A. I would really appreciate if you can reply them there on the Q&A rather than in the session. I'm extremely sorry about that.
Thank you, sir. Mr. Ashish Dayal is also raised hand, so we can take in the question tab, and respective speakers can may answer there. Thank you, sir.
Yeah, I'm extremely sorry, Mr. Ashish. I'm not able to take up your question due to the time paucity. I would really appreciate if you can type down your question. I'm sure Dr. Richard will answer your query. Sorry about that. Can we run to the next session, please? Okay, so next presentation is from Professor Mehdi Banes, who is a very well-known name in the world of telecommunication. Professor Banes is a professor at the University of Oulu, Finland, and he's also heading the ICON Center there. He is very instrumental in distributed AI, 5G, and 6G networks with a plethora of publications, including various prestigious awards which he has received, like LSET Prize, Early Achievement Award, Collaborate, Highly Cited Researcher, etc. Dr. Banes is also an IEEE Fellow. Unfortunately, he couldn't join us live today, but he was kind enough to share his video with us. So, Asif, can we play his video, please?
Sure, sir. Ronak, can you unshare?
Hello, thank you for inviting me to give this talk at the TDD 2022. My name is Mehdi Benes. I'm a professor at the University of Oulu, home to the 6G flagship. So today my talk will be about a new research agenda called Vision X, sitting at the intersection of semantic communication on one hand and System 2 machine learning. So let's start with the state of affairs of 6G. So 6G on the onset promised to bridge the digital, physical, and biological worlds. However, the current visions of more bits per second, more bandwidth, more base station deployment are certainly not sustainable. Taking 5G requirements in terms of packet error rate and multiplying them by 10, 20, 30-fold is certainly not a smart idea either. Taking 5G and just adding AI is also not gonna really cut it, because essentially AI today is brittle, energy hungry, and it's just interpolating a machine, curve fitting, and whatever other techniques we have today. All to say that 6G today is nothing but an incremental evolution of 5G, basically. So you can see it if you look at various white papers. If you check the peak data rate, 5G to 6G. This also reflected in latency, reliability, and so on and so forth. Also, resiliency is ill-defined, sustainability is also ill-defined, so a number of things remain ill-defined. This is essentially where the Vision X comes to challenge a bit the statu quo and flip the paradigm. So here we talk about posing two questions. The first one is, can we transmit less and relax more, and relax some of the stringent requirements of some of these applications? If 6G is really about human-machine cooperation, then we really need to look nowhere else but in humans' modes of cognition, referred to as System 1 and System 2. So these come from the famous book of Thinking Fast and Slow of Daniel Kahneman. System 1 being basically the one that we use today in AI, namely it is just really learning statistics from patterns. It just interpolates and curve fitting. Whereas essentially we are also, as humans, obviously have a System 2 type of thinking, which is slower in nature, plans, and has the ability to handle exceptions and reason, right? So reasoning is certainly not in the current AI techniques. Okay. Now the solution essentially again is at the intersection of two revolutions. So the first revolution essentially is what we refer to as post-Shannon, right? essentially going back to the fundamentals of Claude Shannon in 1948, 49. Essentially here we laid out three levels of communication: level A, level B, level C. Level E is simply about taking a message, encoding it, and then communicating it to a receiver, and then the receiver try to really reproduce X and X. Okay, here essentially no meaning, no context, no structure, everything is removed. Okay, and essentially this is why this communication is akin to just a reconstruction task. In terms of information, this is just a scalar. This is one of the issues essentially of level A. And it turns out it's essentially even Shannon in 52, he wrote a famous article called The Bandwagon, warning us against using only level A as a definition of communication, therefore stressing these two levels of level B, level C. So level B is about extracting meaning from data. C is about acting upon this meaning to solve a given task. Okay, so more specifically in our case, essentially here we talk about agents or control loops, which are essentially modeling the environment, modeling other agents, and reasoning over each other's agents in terms of intent, goal, and beliefs, right? And here everything is emergent, right, as opposed to level A type of tasks. And information here, as opposed to being a scalar, is a topological space. Okay. Also, we can look at it essentially also from the realm of Shannonian is essentially related to statistics. So these are statistical measures of communication, and communication is just a reconstruction task. Contrast that with semantic communication, which also has statistics, but also more importantly, structure. So structure is essentially what is currently missing in semantic communication, but also system to machine learning. So what do we really mean by structure? So structure essentially is whatever remains invariant under isomorphism, right? So this is why typically the question that we should always ask when tackling a problem is what kind of space, topological space, my signal lives. So the signal here could be an image, state, a policy, Markov decision process, and from there on, of course, we have to deal with certainly with statistics and modeling the uncertainty of our, let's say, data distribution, but we really need to bring into the picture is the notion of topology, right? So again, what kind of topological space characterizes my data, right? As opposing to learning in the data space, we need to be able to learn in the topological space. This is essentially where the meaning, the semantic live, right? In order to also manipulate this topological space, we need tools from algebra. But these are really about, characterizing whether different topological spaces are the same, are they invariant to one another, are they part of one another. So this is essentially what we need, right? So today we only have this box here. We really need to talk about algebraic topology if we really want to unlock the revolution in, again, machine learning system 2, but also semantic communication. And here the tasks are obviously about reasoning. So how do you reason causally? How do you reason counterfactually? How do you reason logically? So logic also has an important role to play in 6G, and we haven't seen that yet in any of the current white papers. As I said, algebra again is about merging, multiplying policies. So if you are using, policy gradients, how do you take two policies and merge them together to emerge a new policy, right? Basically reflecting an environment that you have not seen in the data, right? So typically what we're given a training data, and then we train a model. What if you don't have any training data? How can you reuse your knowledge, piece it together to solve a task? That is essentially where algebra comes to play. And also here, which allow us to go beyond current neural network architecture, ranging from CNN or GNN or others, right, which are based on the notion of translation invariance, group actions, going from acting on a set towards acting now on a category. So higher order abstractions is essentially needed in okay. Also, while semantic communication has different definitions, you can see different definitions: rate distortion, compression, goal-oriented communication. There's a lot of confusion right now in the literature, which means that it means different things to different people. Semantic information also is ill-defined. For some people, it means just the importance of data. It means just I need to filter out some data. For some people, it means taking a VAE type of machine learning algorithm and just extracting the latent representation, just semantic information. Also, the notion of set notion of information, which is referred to as the pre-sheaf of Galois group. These are more substantial notion of information because we go from a scalar to a set. And now, if you want to scale it up, you go, of course, what's a group with more structure. Then you end up with a category. Therefore, we say that actually semantic information lives in the category of enriched pre-sheaf. So these are notions coming from category theory or higher order algebra. Okay. Also, logic, as I mentioned, logic has a very, very important aspect, but again, that naturally comes from when we talk about shapes of information and what kind of topological spaces we're dealing with. Okay. Of course, on the AI, of course, front, as I said today, we are obsessed with accuracy. The problem of energy efficiency is really there, the carbon footprint when you train a model. But to me today, my focus really is on these two. Essentially, the current system one machine learning are basically unable to reason, unable to extrapolate because they don't learn concepts. They don't learn any abstraction from data. So we came out with these 6 desiderata here that you see. So one, the semantic representation has to be function of the data. It has to be minimal, meaning compressed, but it also has to be, more importantly, invariant, disentangled, causal, emergent. So invariant is really this notion that I was telling you today. What kind of group action it will essentially be acting on the set of images or videos or any other input that you have, that such that the output remains invariant or equivariant, right? This is exactly what we're after. In fact, what we're trying to do is kind of a Lego learning, meaning decomposing these concepts in terms of repertoire or sub-concept, and then combining these sub-concepts together so as to solve a given task. We haven't, again, seen this yet. And then, of course, what we need to do as an objective is to learn semantic representations satisfying the 6 desiderata for X. So X could be training a model, could be inference, could be any other type of task you have. Okay. So now what I want to do now is really just to deconstruct a bit the system 1 semantic communication, which we see today, which is already implemented today, versus the much harder one, which is called system 2 semantic communication. So what system 1 semantic communication? System 1 semantic communication is really operating in data space, meaning I give you an image, you apply your CNN, you extract a feature, you communicate the feature to the receiver. You could also try to be a bit fancier, meaning that now you have an image of a dog. Now what you want to do is to take one modality, translate it in terms of another modality here. This is text. Communicate that text over wireless, and then at the receiver generate a different dog, different X. But this is really still very basic, because essentially here the task is still reconstruction task, and the representations are just dealing with D1, D2. We don't have any invariance. We don't have any disentanglement, right? We don't have any causality, obviously, here in the model. This is purely statistical model. But again, this is what we are doing. Okay. Now, system 2 semantic communication builds on system 1 semantic communication. So you can look at it through the lens of the 6 desiderata. So now we have the invariance here, right? We have the disentanglement, we have the causality, and then we have the emergence. In terms of goal or task here, we need to deal with compositionality and reasoning and extrapolation. So compositionality is really the key here, which we do not have and which we need to really go after if you are really serious about, talking about human-machine cooperation, communication between machines. We need this kind of abilities going beyond just pattern recognition. Okay, so with this, of course, you can tackle a number of use cases. So here, for example, you have robotics use case in a factory. A bunch of robots want to communicate. So what are going to be their symbols? What are going to be their semantic representations so as to solve a goal, right? So here we talk about the syntax of this language. What is going to be the syntax which is going to be different from a 3GPP language? Also, here we have a base station users setting where now the base station is trying to teach a language, of course, pre-existing language to a bunch of users here. How can it do it in such a way that the language it teaches them is actually generalizable, right? Has some sort of compositionality, such as the new users that are joining the network can learn, pick up the language, right? And again, there are many other use cases. But what's important now here is we need to have the notion of agency. So these are control loops. These are dynamical systems interacting in the environment, right? We also have the notion, as I said before, abstraction is very, very key, right? And compositionality, as I've been stressing out. So let me walk you through 2 kind of baby steps, works that reflect a bit what I've just said. So the first one is really about semantics native communication. Here I have 2 agents that want to communicate. So I have a speaker, I have a listener, and they want to really to converge towards a mutual context, which will be tantamount to them having really successfully communicated, right? So what we do have, again, this is my speaker, this is my listener. Now, what we typically do is we take an input X here, right? And then we just, again, encode it and then communicate it to the receiver, or maybe communicate X, right? Now, if you do that, then of course you'll not be able to generalize. Instead, what you need to do is to go from your space X here to a concept space. This is what is reflected here, where we use the notion of triangle of meaning, right, from linguistics. So here you see you have again the 2 agents, and you have now the observational space. This is the data space X, let's say, right? And then what we do is we map it to a concept space, right, which is going to be more general than just the observational space, right? And this is what is going to be now communicated, right, symbolized, and transmitted to the other listener, and then the listener is trying to infer the intent of the transmitter. So this process again will iterate until they converge towards a mutual, again, concept space. Okay, so mathematically this also can be formulated. This is a loss function of the learning. This is a joint entropy of the speaker's context. This is the mutual context where they want to converge to. This is the entropy of P, and likewise for the listener. So you can show that actually this algorithm does converge over time, right, to an optimal solution here. What's interesting to show here, for instance, is if you compare the semantic representation length, right? What's the payload communicated over wireless? Comparing, this is a system one approach. The system one approach is just, you know, kind of communicate all the semantic representation, all the concepts. So the X extract all the possible concepts, communicate them to the receiver. Whereas system 2, it communicates the minimum amount of semantic representation such that the receiver, the listener, is able to infer the intent. So kind of a game between the speaker and listener. So we can see here essentially that really over time, we are able to reduce significantly the payload of this semantic representation. If you also look at reliability, this is semantic reliability as a function of this alpha and beta, which play the role of really compression here in concept space, right? So you can see here as you go from t equal 20 to t equal 200, you see that, you know, you have higher semantic reliability, right, at the cost, of course, of time. So this tells us that there are a lot of now interesting trade-offs in terms of computation reliability, semantic reliability, and latency. Okay, so this is a bit what the first work. Now moving on beyond just two agent case to multiple agents. So now what we want to do is to learn generalized MAC protocols via abstraction. This is a very, very interesting topic which I think will come to really disrupt a bit the way that agents communicate today. Okay, so the question was, can we learn communication protocols from data across various use cases, applications, and so forth? So here we start from the work of Jacob Moiris from Nokia, when he was in Nokia before joining NVIDIA, which is a system 1 MAC. Essentially what he did is he just took the 3GPP protocol and then replaces it by a MAC learner and let the agent learn by iteration from data the rules of the game. Here the rules of the game, meaning you have the scheduling request, scheduling grant, acknowledgement, and so on and so forth, entirely from data. So they use this idea of multi-agent RL and learning to communicate module, and then they show essentially that it works. However, this idea has, a serious caveat by not generalizing. And the reason why it does not generalize is because it has no structure. There is no invariance. There is no nothing that will allow this policy, this model to generalize. Once you add more users, you change the frequency range, and so on and so forth. Okay, not to mention other kind of caveat here in terms of a limited number of vocabulary, few users. Okay, so we took this idea and we said, okay, let's now apply this idea of abstraction. Let us not learn in the state space, because that's the space where it is noisy, which is gonna take a lot of time to convert. Let us now compress, project, learn the space of information, right, where we will be able to learn our policy. So essentially, policy gradients will be learned in this space here. So now, of course, how do you do state abstraction? You can compress the states, you can reduce the cardinality, you can leverage some sort of symmetries if you have it. Here we just reduce the cardinality of the space, and we actually did that by really just using the rollouts or trajectories from reinforcement learning to learn a latent representation Z here, which allows us to generate at will different basically different trajectories, which we can now, or signaling if you wish, which we can now use to either pick up the best according to the situation, or maybe combine them, or other type of idea. Okay. And we actually compared our solution here. This is the total number of delivered packets, total number of users. This is the baseline without abstraction. This is Q-learning approach, and this is our approach. So you can see here is a huge gap in terms of performance between abstracting and no abstract. So abstracting is really, really a key essential ingredient we have to leverage in all type of learning. So this was one example, right? And of course we can push this further. Now what we can talk about is neurosymbolic protocol learning. Why? Because essentially if we just use neuro protocol, this again will not be able to generalize, because essentially they don't learn, they don't understand. So what we need to do is to translate, map this NPM neural protocol model to a symbolic protocol model, SPM. So this transformation here is really key in order to compress the knowledge, map it to an abstraction, which we can then use to manipulate algebraically to essentially communicate right, coordinate with other type of agents. That is essentially the high level view of the idea that we have in mind. And we have actually done a very early work here, essentially leveraging symbolic protocol to avoid retraining a policy when you have new, when the environment changes. And it will actually work very well. But the goal here is really to essentially analyze protocol, what makes them generalizable, what are the features that play this role, right? Can we compose, rank them, compare them? Again, this is the goal here. And this is essentially just bringing me to the end of my talk. This is just again a summary of what Shannon, what semantic communication. So I hope you understand now that in the case of Shannon, information is just a scalar. So this is really a scalar is not really something that we allow you to learn, let's say, robust policies. Instead, of course, what we naturally need to use is this information structure. Where does my scalar, where does my entropy live? If we do that, we are able now to learn much robust communication protocol, but also even machine learning model. And again, here what we need to do is to go beyond reconstruction as a communication task, but to reason, right? So we need to reason about object relationships. We need to reason beyond the set of observables, because sometimes there's no information in the data, and therefore how can two agents, two databases, two gateways, two base stations, two drones are able to coordinate? So this is definitely the way to go about it. And really, with this, thank you very much. Just some takeaways here for industry. So to please facilitate data sets, simulators, algorithms, competitions. Otherwise, there will not be no leap in this area, right? So every person recodes every time from scratch the algorithm of other papers, because essentially the authors do not share any source code. We have gone through that. It's really painful. And of course, from an academic perspective, we need to build bridges between multiple disciplines. This vision here is beyond communication, is beyond machine learning. It really involves mathematics, abstract logic, abstract topologies, algebra, control dynamical systems. So this is the only way if we are really, again, serious about making leaps beyond what we see today.
Okay. Thank you very much. I mean, this was a very engaging talk, and I really wish you were here. I'm also seeing there is a lot of activity on the Q&A and the chat. Unfortunately, we are limited with time. We had a fantastic session ranging from the start that what should 6G be. We touched upon the air interfaces. We touched upon the the cell-less stuff which Professor Demir spoke about. I mean, very engaging. A lot of questions I see on the Q&A. Very interesting thoughts. Followed by Mr. Richard, who spoke about the convergence of the mobile and the cloud world. I mean, not an easy concept to be picked up, but I think all of us are becoming interdisciplinary in the days to come. And followed by the semantic communication, which I see is probably 6G and maybe beyond 6G as well. I don't really know that we'll be able to realize it anytime soon. And I'm sure if he were around, we would have had a lot of questions around it. But I encourage all the participants to send out their queries to us or directly to the speaker, and they will be happy to answer that. Without much, I'll probably let everybody know that TSDSI is actively involved in ITU. We have been participating very significantly, both in the vision, the future technology, the roadmap which ITU is working upon. We are also deeply engaged with 3GPP. A lot of participations happening in 3GPP at different working groups, SA, RAN, and quite some participation happening. TSDSI invites everybody to be a part of it, whether you want to come and participate in the standard building process or you want to create more forward-looking technologies with the help of the roadmap committee at TSDSI. So with that, I would like to thank all of our speakers who spared some time, and also the speakers who could not make it to this session though, but they spared their time to present their videos, which is equally challenging and time consuming, I know. And all the Q&A which has been answered on the Q&A box and the chat box, and a lot of questions which I could not even take up. I would have really loved that we had some more time. And I have to really rush through because we have another session to start up now.
Chair, may I interrupt? If I may, Mr. Sushil Kumar raised his hand. Please guide us.
Okay, maybe I'll give him strictly 1 minute if he wants to talk for his question. I mean, not more than a minute because 4:30 we have to close sharp.
Yeah,
Yeah.
thank you,
Then
sir. My query is that for the networks beyond 2030, like the focus group on network 2030 and study group 13, they were speaking about the IP's new IP scheme. Whether the IPv6 will be sufficient for the 6G technology or some new IP concept that was being discussed in TSAG as well as focus group network 2030 or the study group 13 that will be required for the network. What's the opinion of the expert speakers in this session? Thank you.
Okay, interesting question. So whether Richard would like to take that up from a cloud perspective, I believe.
Yeah, certainly. I must admit it's not. It's a quite specific question. It's not one I've really considered. I think I'm probably working on the assumption that yes, it will be sufficient, but I don't say that with necessarily with any really careful consideration to the question. But I think it's a very valid point that is something we probably do need to look into and confirm that assumption is valid.
Sure. Thank you. I may probably add with my small background with IETF. IETF believes that IPv6 should be enough. At least they don't see that running out of the problem in any near future. I mean, at least not for a decade or two, at least. But as Richard mentioned, it's definitely worth investing into, and especially if a new architecture emerges for internet, like information center networks and all, then probably we might run into a challenge. So, but definitely a very valid question. So,
Okay, thank you.
right. So thank you very much. Thanks a lot, all the speakers, everyone. And I would like to spare a minute to thank Mr. Mittal, who helped in orchestrating this entire session, and also my co-chair, Mr. Prakash, who was instrumental in taking care of all the smaller and smallest nitty-gritties for this session. I would also like to thank Ronak, Akash, Asif, and all the entire team from the air meet. And also I'm seeing a lot of people who are involved backstage, the TSDSI team like Jaskirat and everyone. Without them, this would not have at all been possible. So I really thank all of them for the wonderful show. And once again, the audience, without that, this session has no meaning. So thank you very much. Thank you all. So over to you, Mithil sir.
Yeah, so thank you very much, co-chairs, Mr. Prakash and Mr. Samar and all the speakers. And here we had a very wonderful session. You have nicely summarized that. We wish that we had more time and to hear the answers to the questions, because questions were really interesting. They would have, expanded our understanding more about what has been said. But maybe in future, because TSDSI keeps on holding events, and we would like the speakers to come back again and we are to hear them. So thank you very much for sparing their time joining here. Thank you very much.
Thank
So
you.
we can close the session.
So do we have a quick photo session as well, or?
Yeah, Asif, can you run that photo session?
Yes, sir.
Okay. Yeah,
I
that is a
will.
great idea. I just probably missed that. Thank you so much for.
I don't want to miss my speakers,
I can pin if speakers may. Prakash sir, can you? I can. Four would be on main screen. One by one, I'll take 2 or 3 photos. Let me just do that. Also, Raunak, you may take photos.